Anything else from homework stuff?
On the number 60 for 3.1 on the part B, do you want us just to like draw a graph and prove that?
Number which? Where?
60 part B
60?
on 3.1.
3.1.
It says like prove that 2.7 doesn't go through.
Yeah, if you do the math the same way we did in part A, it'll come out to have no solution.
Exactly.
And then the answer, I mean, where could I put a point so that there is no tangent line to a parabola that goes to that point? So you can imagine tangent lines go like that, roughly, very roughly. So we'll capture every single point that is outside. The minute you put a point inside, there's no way it could be tangent to the parabola. All right. So that point that they give you in part B, 2.7, it's inside the parabola. So if you try to do the calculus, it'll come out with complex answers, which means there's no real solution. Okay. All right. Yes.
3.81.
Oh yeah. This is a cool one. I like it. Cepheid variable star. Blah 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 blah. All that business. It's really cool shit, but do you need to know all that? Not really, right? This is math class. You can just focus on the math, but it's cool to know the idea behind it. They give you the function, and the thing to realize about this function. So this is number 81 and 3/4. So 55.4. All right. Shoot. This derivative is remarkably nice. What's the variable in this case? And they tell you, actually they write it better. They tell you directly what that is. It's b of t. If I had to guess, the only thing that could possibly be the variable would be t. That probably stands for time. So if I take a derivative, it's going to be a true rate, like a rate per time. Brightness, I think it is. Yes. Brightness is crazy. So the mistake people make, bless you, is what's going on inside here. I mean, why is this going to be a chain rule? You know, it's in that section, so you know it's going to have to be. Why is this a chain rule? Because this thing inside is not just t, it's something times t. But what's the derivative of sine of 4t? What's this guy's derivative? Yeah, it'd be like cosine 4t times the derivative of 4t, which is 4. So if I would have put a 5 there, it would have just been a 5, right? You with me?
Yeah.
So if I put a 2 pi over 5.4 there, it's going to be 2 pi over 5.4, blah, 2 pi over 5.4 t. Whatever the coefficient is, it's going to end up sort of coming out. You guys kind of with me? We see that with a few different, whenever the inside function is linear, there are easier little shortcut rules. For example, what's the derivative of this? What's the rule? E to anything, what's its derivative?
Z.
Itself, right? Thank God for E. And then what happens? The inside gets in derivative of 7x is 7. So if I would have put an 8 there, it would have come down. And it's not really coming down, it just looks like it is. You guys understand what I'm saying? So e to any linear function, its derivative would be a e to that. The a sort of comes down. It looks like it does. You can make a little rule. The mistake, you guys all with me? If I do this derivative, what do I get? I get itself times the derivative of this. And what's the derivative of this? A. So the mistake people make is they extend this rule too far. They say, well, anything up there, then the first number is going to come down. Yay, and that's bullshit. The only reason it worked that way is because the derivative of a linear function is its slope. It's a singular thing, right? Singular? I can almost say it. So if I had this instead, Is it going to be 4e to the 4x squared?
Just 4.
Hell no. So g prime is itself times the derivative of the inside. And what's the derivative of 4x squared?
4x.
8x. You see what I mean about extending a special case too far? People take that and they say, oh, it's always going to be. No, it ain't. You always want to apply the rule unless you get really, really comfortable and realize exactly when you can do a shortcut. All right, cool, maybe. All right. Yes?
So, how would we take the derivative of p of t? It would be 2.5 times 2.5 cosine.
Notice something very important. I'm not done here, right? Times something. The inside of the function that I'm taking the derivative does not change. I can't do a double derivative. I can't do it all at once. It's the derivative of that function of that mess, which is cosine of that mess, times the derivative of that mess. And what's the derivative of 2 pi t over 5.4?
2 pi over 5.
2 pi over 5.4. The coefficient. Sorry. You guys like, I gotta get ready for calculus. I understand. Some of this stuff makes more sense, actually. A little bit. Are you guys understanding what I'm saying here? I mean, I could load something down. What's the derivative of sine of square root of 11 pi e to the b? Or let's say e to the e squared over natural log of 2x. What's that guy's derivative? Cosine of that times the coefficient, because the derivative of number times x is that number. You guys see? You got to start realizing this. What is this? This is a number. Is it a nice number? Well, some people might think it's nice, but
It's ugly.
I think it's going to be kind of ugly.
But it's got a lovely personality.
And yeah, you can look at it two different ways, but no matter, it's a simple number. No, we can all agree it's not a simple number. Right? But you got to start realizing that that's just a number. That's so important, obviously, because then derivatives are easy of them, and they are just numbers. So when they're just coefficients of linear functions of x, that's going to be its derivative. It's going to be times square root of 11 pi e squared over natural log of 2, because the derivative of this is just going to be the coefficient. Bless you. Cool. I'm glad I had orange juice this morning. You guys are scary. Vectors. You're all vectors. Alright.
How do you do the second part of that?
And then part B, the rate of increase after 1 day. So you've got your b prime of t, so then you throw in a 1. Let 1 day pass and see what the rate is now. Cool. So this, when you plug a 1 into this, what does that tell you? Well, you guys don't know what's going on in this problem. It's about a star's brightness over time. So when you plug a 1 in here, and it's in days, so what would that represent? T is 1, so what would the answer, if I plug a 1 in for t, the answer means what? Don't tell me what it is. What would the answer mean?
Brightness.
The brightness of the star
After a day.
after 1 day. If I plug a 1 in here, what do I get?
The rate of increase of the brightness.
How quickly the star's brightness is changing after 1 day.
Or
Do you guys understand? And what might get more interesting, actually, is doing like a brightness over distance. Or like sound, like when you have intensity over distance. When you have sound waves coming out, they have to cover the inside of a sphere, which is why you have the inverse square law. Have you guys ever heard of that? As you go away from something, the sound has to cover the area inside a sphere, so it goes down by the square of the distance you are away from it. What the hell am I talking about? I don't know. Shit. But if you did a brightness per distance, you could say how quickly is the brightness dropping off as you get further away from the star. That's more interesting to me, but I won't.
How do you do setting 2.4?
Oh, cool. I like it. If you did the practice test or looked at it, there's a big chunk of the problems that look a lot like this. So that should be sort of a clue about something. So if I know f of x is xg of x squared, is it? Yes. Find f double prime in terms of G, G prime, and G double prime. That sounds horrific, but what you just start doing is just start doing it. Don't think ahead about what's supposed to happen. Just what's F prime? What's the rule? What's the main rule going on here? Can you guys see that? What's the main rule? Product rule. Do you guys see what I mean by that? It doesn't matter what's in there yet. You don't have to know it all ahead of time. I think that's what throws people off. Some people have trouble. They think they're supposed to know ahead of time what's going to happen. No, shit, I don't know. I don't let myself even worry about it. Because then I'm like getting stressed out. No, it's just a product. That's right. It's like Seinfeld teaching calculus. It's just a product. So the rule is x prime g of x squared plus x g prime of, let me just say it like this, g of x squared. You can do it, Jeff. Prime. Right, that's the product rule. And now I can attack all the pieces. So this is easy. Good. So we get g of x squared plus x. Now what happens here? G prime of x squared times the derivative of the inside. Good. All right, that's the chain rule. And real quick, just to make sure, because I still get people that will do this. I'm sorry. Because they don't know where to stop. But I always thought that's such a weird thing. If you have any trouble with that, don't skip any steps. Write the rule. Does this involve a chain rule? Officially, no. We kind of know it always does. But no, nothing's going to show up. It's just an X inside. It's not something different. So there's not going to be another link on the end of this. That's the end. After I do that derivative, I'm done. There's no where do I stop, Jeff? That question should not come up. Unless you're not showing yourself the rule. Then you're just kind of guessing, I'm going to stop now. Show yourself the rule, then you'll know exactly where to stop. All right, Jeff, you just did the whole damn problem, Jeff. All right. Times 2x. So then you can write this as?
3x. Or x, 2x squared.
2x squared. Right. So little things like that you better do, right? Yeah. You can do it on your paper.
So when it says in terms of G prime...
I'm not done yet, right? Because they want to know what G double prime is. So now just keep going. So now this is, what F double prime. So this is F prime, right? Yeah. And now, so let me write it again. This is where I'm going to stop with this, but you guys get the idea. Do another derivative.
So this means that you'll end up with a G double prime in your answer.
Exactly. I like it. And that's what they meant by in terms of G, G prime, G double prime. They could all show up in your answer. Cool. So you didn't have to know ahead of time where they were going to go. They're just going to fall where they fall.
Yeah, I thought you had to find G prime.
No. Hell, you're right. The way they word it sounds weird. But once you start doing some of these problems, you're like, okay, that's what they mean. Do the derivative, and then those things should show up. Yeah.
So that's a key to the first, right? On the
Yes. Yes.
It's not a G prime.
No, it's G prime. Yeah, it's G prime. G prime. Cool. Do you want to do the next steps? Let me guys on.
Yes.
All right, do it. See, that was easy. You want to do it? You do it. So if I do F double prime, this was easy, right? You basically already did that.
2x times G prime.
Yeah, 2x times what now?
G of x.
No.
G prime.
Derivative of the outside times the derivative of the inside. Plus, now here, what's going on here? And look real quick. I don't know if some of you guys can see this. Isn't that almost the same thing we had to start with, sort of, in a way? I mean, it's not quite the same enough for me to make this point, but derivatives repeat a lot. Right? You start to see that, especially with some certain functions, they repeat a lot. But what do I do first here?
2x squared.
Derivative of 2x squared is 4x. Leave this one alone. Plus 2x squared times the derivative of this. Well, what's the derivative of g prime x squared? G double prime x squared times the derivative of the inside. I mean, there's no way to know ahead of time. There's no way to know ahead of time how things are going to shake out. And the way they word the problem makes it sound like you're supposed to, but they just mean do it and see what happens. So every step I took, I was motivated by the last step I took. It tells me what to do next. When I write the rule, I know what to focus on. I write the rule, I'm like, oh, I haven't done that derivative yet? Shit, I better do it. So I'm not up here just knowing what to do next because I know math. No, I know the rules. I'm applying as much as you know. You know the rules, supposed to. If you write the rule, it tells you what to do next. People that make the most mistakes are the ones that don't write the rules for themselves. They're like, that's a waste of time. Well, it depends on if you want to pass. Okay. Yes?
77, 3.4. I was just thinking, is it the same as our previous homework?
Yeah, whenever they say especially when they say find the nth derivative, but if they say find the 50th derivative, the 800th derivative, my God, I haven't had anybody do this yet. Don't turn in like pieces of paper, sort of like the shining moment. You know, all work and no play. And they're checking, no, don't do that. I'm doing my 800th derivative, Mom. Leave me alone. Labyrinth outside or something. Sorry. But anytime they say find the 50th, 100th, whatever, do the first few, and then you should see a pattern, right? So in this problem, it says find the 50th derivative for, which one was it again?
77.
77. 3, 4. Y equals cosine 2x, find the 50th derivative.
So find first 2 or 6.
So what's y prime? What's the root of cosine?
Cosine, sine.
Negative sign, thank you.
Minus
2x
2.
times 2, good. What's y double prime?
So negative 2.
Yeah, negative 2, what's the root of sine?
Cosine.
Cosine. Root of 2x?
2.
2. You guys, a couple more should get you. Because what are tricks? If I start with cosine, the derivative of that would be negative sine. What's the derivative of that? Derivative of negative sine.
Cosine. Minus cosine.
Negative cosine, what's the derivative of negative cosine? Beautiful. Negative sine. So sine. So it starts over again because the derivative of sine is cosine. See, so it sounds like you maybe have to do about 4 or so derivatives to really see the pattern of this, possibly, or else you just know this. What you're really interested in, what's the pattern of these? But every time you do a derivative, you're going to pick up a multiple of 2.
So it's going to be 8 sine.
The next derivative will be
Minus
derivative of cosine is
Negative sine.
negative sine. So negative goes away, and the 2 comes out.
So it's
8.
Sine.
The inside is a linear function of x, right? Which makes me think there's a quicker way to do this. Right? Every time I take a derivative, I'm going to pick up in one of these slopes. It's going to come out, right? Multiply by its derivative, so its slope is going to come out. Does this make sense? A little bit?
How do you capture like the negative change in like a rule?
Well, that would be difficult if they ask you for the nth derivative. That would be difficult. I'm not going to argue with that. You'd have to describe it in words, actually, so it's not easy to do mathematically. Here, they just want to know what the 50th derivative is, so you just have to know yourself when is it going to be negative, when is it going to be positive.
By like every third one.
Maybe, something, right? What have we got so far? In the second and third ones, it was negative, right?
Third and fourth will be positive.
Yeah, and you can try to capture. So you don't have to get a general rule written down. You just got to figure out a rule for yourself. So you know the 50th one is going to be something. Done enough of it. You guys can keep going now. You should not have to do 50 derivatives, my God. So maybe at most do a couple more, maybe, and then you should have enough information to figure out what the 50th would be. All right, so what I want to do, I don't think we ever did do the ones at the bottom. I think I gave this one out at the end of last class. We haven't talked about the ones at the bottom here. So I want to focus on chain rule for the rest of the day.
Is it increasing by an exponent of 1 each time? Technically?
Say again?
increasing by an exponent of 1 each time? So it'd be like 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power.
Yeah, it looks like you're going to have a 2 to the n, if you're trying to think of a general rule.
Yeah.
Yeah. Sure. I guess so. All right, so it's the last couple things. The first couple problems are done for you. They're just examples. So if you have this paper, if you look in the little box where it says the chain rule, I like the way it's written with the d by dx notation, right? If you can make sense of that, that's pretty good. So maybe as soon as this gets up here. I'm talking about this right here, this piece. So this is kind of cool. Dy dx is dy du. So if I had, what they're saying is let g of x be u. So if I have, for example, e to the 4x squared minus 7, I can write that as e to the u. Well, I guess u. Then the derivative of e to the u is e to the u times the derivative of u. So look what this is saying. This is saying this is the derivative of the function with the u in it times the derivative of the u piece by itself. That is the chain rule. So when it's written like this, it actually makes more immediate sense, to be honest. I just, for whatever reason, I haven't really used this notation much with you guys. I have to force myself to kind of do that more often. In physics, we start using stuff like this. The dots represent derivative with respect to time. Right? But anyway, sorry. And that's the one, that's this form we've seen it in before. That's the form I used to prove it the other day. Okay. So I give you a couple examples. And we talked in class, and I just have to say, I love the way I showed you, because I was never shown that way, which is beautiful. Which if you assume that it's supposed to work the same way as always, the 3 comes down and becomes a 2, and that's all you can think about, it should work the same way if you multiply this thing out. And that's how we discussed it last time in class, right? We did that. We actually foiled that bad boy out, and we did the derivative. It's got to be the same derivative, and they weren't the same. So therefore, my assumption that the same rule holds must have been false. There's a slightly different rule, or a more robust rule, the chain freaking rule. And it's the part that picks up the part that I was missing. So this is sort of like gears might work. I'm always trying to come up with a nice physical analogy of this. But the outside is moving at a certain rate, but so is the inside. The inside's moving at a certain rate. So those two rates have to interact with each other. That's why you multiply by the rate of the inside also. It's making the whole system move faster if it's moving faster. So the most important thing with chain rule is identifying what the inside is and what the outside is. So this first one's not too bad, right? The 3 comes down, second power, and then the derivative of the inside. Cool. So what about number 3 here? This is a pretty nice, but
1
good.
3 cosine.
1 plus 3 cosine.
Yeah, so if you did the derivative of sine is cosine,
Oh, that's not.
And 3.
and then times the derivative of the inside. So you get 1 plus 3 cosine 3x. I like it. Cool. I like it. So like I said, the chain rule is the reason the shortcut works. So if the inside is just linear, you multiply by its slope. Because that would be what the chain rule would give you. Maybe. So what about this bad boy? That's yummy.
So
What's the outside function? E. I love it. So derivative of e to stuff is what? E to stuff. So let the first step be easy. Times, now you take the derivative of the inside of the stuff. zoom out a little bit. So the rule for E is it's itself, but then the inside function gets its own term. Right, it's very similar to product rule where you give each one its own term, but there it's addition because they're separate already. This one is inside the other one. Well, that's freaky. So I get e to the 2 sine of 5x squared minus 4. And then what happens here?
Use general, yeah.
Yeah, and again, you don't have to know ahead of time. I'm sorry. You don't have to know ahead of time how often it's going to happen. But I get twice, what's the derivative of sine? Cosine of stuff. Times derivative of this. What's the derivative of 5x squared? Minus 4. 10x. Cool. And then you just pull that 10x. Just come out front. Right? That's the last little simplification you can do. Multiply it by whatever's there. Nothing's there, so it's just 10x. If you didn't move it out there, it's not a big deal. But if there was a 2 out here, you got to bring it up and make it 20x, right? I mean, you just got to do that. But there wasn't, so it's okay. All right, how are we feeling about that so far?
Could you pull a 2 off the cosine and multiply by 10x?
Oh yeah, this bad boy is not to a power, so yeah, the 2 can come out. Yeah, there you go. So you get 20x e to the 2 sine 5x squared minus 4 cosine 5x squared minus 4. Yeah, cool. I like it. So what I have is another little sheet.
Are you going to give out the answers to the practice test?
I wasn't going to get you guys started with this. So don't forget what's tomorrow. Tuesday. It's what's happening tomorrow. Review, cool. And then the next day it's the test day. So I do have the answer key. I'll give it to you before you leave.
Test is going to be up to 400.
Yes. So go ahead and try these out. You can work together if you want to. Cool. And then just bring the pie out front. Or you can leave it back in. Yeah. Yeah. Yeah.
So, numbers, like first one, C, is it like AX? A in all caps?
What is it? Pi x. Which one? C? 3 to the x squared.
Is it going to be like this?
3 to the x to the second power. The triple decker.
Okay.
Yeah. So the power of 3 has its own power. Right? I'm raising 3 to the x squared power. Yeah. Cool. See the inside function? Stay the same. The inside function stay the same. Inside function always stays the same. When it gets its turn, it changes. But you're also missing one thing because the base is not E. Yeah. Oh. That is our power. Looks like
Oh,
yeah, yeah. Change goes to secret. Go change goes to yeah. And then cosine, into that, negative sine of that, not sure. Yeah, I like this.
So it's like, leave the x,
It is like a freaking